Hi guys, I'm Martin Dube. I'm from Chernobyl.com. This is Martin Malik, our speaker today. We're from the company Chernobyl.com, which obviously means that we're doing something with Chernobyl. We're a tourist company. We're in the business for 10 years. And this is the very first time we actually decided to do something as a webinary. What we try to do, what our mission is to spread the Chernobyl story, to spread the legends, but to spread the stories of the heroes and to basically tell the story of what Chernobyl is and what happened and what there is right now. Besides doing tours where we're explaining everything, we're also doing travel cinemas and we're taking part in numerous exhibitions around European cities. And so we decided to spread the word and spread the story of Chernobyl even more. And what better way to do it than via internet and webinary. So this is the very first time we do it. I hope you'll enjoy it. And basically, feel free to ask any questions. We're here to answer it. As you all know, Chernobyl will have an anniversary, a very sad anniversary on Friday, 26th of April, which will be the 33rd anniversary of the catastrophe. That's why we decided to do the webinary now, to tell something more about the story. So Martin here will tell us a little bit more of what actually happened on that night and what happened in the upcoming days, hours, and even weeks after the accident. So, Martin, feel free to start.
Thank you for the introduction. So, I'm a person who is really interested in the accident, and I have tried to summarize the most important actions and what happened during the problematic night, during the explosion. At the beginning, I want to say that there are several documentary movies, several resources on internet, and a lot of information is unfortunately not quite true. So what I tried to determine was what really happened, and I analyzed a lot of sources, a lot of material. Most of the material is unfortunately only present in the Russian language, and I'm not aware of any translations to other languages, so it wasn't an easy task. So I hope you will enjoy this presentation and learn something new, perhaps something that you have never heard before.
So to tell a little bit more about ourselves, I'm working for Chernobyl.com. I'm the managing reactor, so basically running the company, trying to spread the word the best I can. And Martin here is a former tourist, so he was actually for the first time in Chernobyl as a tourist, and he I would say fell in love with the place. He got so much mesmerized by the place that he started to search about the place, even before his tour and even more after his tour. So he's the guy that took enormous number of hours to go through the Russian and Ukrainian archives, to go through archives that are only in Russian, even though he doesn't speak Russian, or now he actually speaks a little. So he took all the energy and all the power to basically tell us what he found out and what the real story is. So that's why we're super thankful to him, and he actually taught us a lot, even much more than we even knew. So I hope you really enjoy it, because this is the very first time and the very special time you can learn something especially great.
Okay, so let's start. So as first, we will talk a bit about the power plant in Chernobyl. As you can see, there are 4 blocks. This entire power plant consists of first 2 blocks that were of first generation reactors, and then block 3 and 4, which were of second generation, which was a bit newer with some improved features. Here we can see of the 4th block. At the center of the block is the nuclear reactor of type RBMK. We will talk about this a bit later. This part is the turbine hall, where the generator for electricity was placed. And other important places were, for example, the drum separators, where hot water from the reactor was separated, steam from water, and then passed to the turbine. Then main circulation pumps, which were 4 of them on each side, and these were pumping the water into the nuclear reactor from the bottom. From the inside the reactor, the water is heated by as nuclear chain reactions are happening, and the heated water is then from the upper part transferred to the other separators.
If I can ask, how big is basically the structure? How big is it?
It's quite large. Here you can see the measures. This is in meters, so 50 meters tall.
Oh wow!
This building. So it was really a large facility, and just to walk through all the premises inside, there were several dozens of different rooms inside. It took a lot of time to inspect this or walk through it. So here, what we can see above the reactor is the central hall, and this is the refueling machine used to pull used fuel or outside of the reactor and feed new fuel inside. So we can go further. This is a section of the nuclear reactor. This reactor was named RBMK 1000. It was a quite special type of reactor, which is not commonly built in usual countries. This type reactor was actually built during the early days of the atomic age. It's a graphite moderated reactor.
What are the earliest days of the atomic age like?
This is in the 40s and 50s, where there was a strong desire for producing fissile material for atomic bombs.
Oh,
so
okay.
During the early days, there were the first reactors constructed were of this graphite moderated type. And this was a bit similar to these. Nowadays, there are different types. Most common reactors, the boiling water reactors, but this worked on a slightly different principle, and they are not so. The features of those boiling reactors are not so dangerous as this type of RBMK reactor.
Does this type of RBMK reactor still work somewhere around the world?
Yes, I think there are still a few of them working in Russia.
In Russia only. So
the Chernobyl power plant, they shut down all those reactors. As we have seen, this is the commissioning year. So the first in 1977 and 78, and this is the shutdown year. So the last reactor in Chernobyl was shut down in December of 2000. So this type of reactor was designed by Niket organization. This was the chief designer of the reactor, and then a scientific advisor, the Kurchatov Institute, headed by academician Alexandrov. So we will talk just a bit. I don't want to to talk too much about technical issues. So the core of the reactor is constructed of graphite blocks through which are technological channels penetrating. Each of those blocks is penetrated by either a technological channel which contains uranium or control rods and other measurement systems. At the bottom of the reactor is the lower biological shield. This is this OR called. Here are the feed water pipes. So the cold, or relatively cold water.
What does it mean? What does it mean, cold water? What was the temperature?
The temperature is lower than the here, but actually the temperature is at the inlet of reactor is 270 degrees of Celsius, and at the upper part of the reactor 284. And there is also a difference in pressure. And this difference in temperature and pressure from the inlet, between the inlet and outlet, generates the steam, which is then fed to the separator. So inside this core, there is there are nuclear chain reactions happening, and this must be, of course, controlled safely so that an accident won't happen. And this is a quite complex process because there are several factors that are influencing the stability and the entire system. So it's not as simple as described in some, perhaps, I would say, some documentary movies. So this is a quite complex system. The reactor core is covered by the upper biological shield. This is the famous lid that during the explosion was thrown out of the reactor and then landed back in an inclined position on the core of the reactor.
How heavy is it? Do you know?
There are different. There is really different information from, I don't know, few hundred tons to up to 2,000 tons. But I think the approximate weight of this shell is about 1,000 tons.
And it was thrown away during the explosion.
Yes, it has flown.
Amazing.
Vertically, and it's called the Elena. So that's the Russian nickname for it, because the abbreviation for it in Russian is E. So this is the E scheme, and this is the OR, but it's not so important now.
Okay.
So a few technical parameters about the reactor. Power of this reactor was 3,200 megawatt. This was a quite high power reactor.
Is it a strong reactor compared to today's reactors?
Yes, it is a strong one. The power is a few degrees
so
more.
Even today it would still be a really powerful reactor.
Yes. And we also need to say that this type of reactor was constructed because it had some dangerous features. And some might ask why such type of reactors has been built. There were several reasons for this. One of them is that this type of reactor is relatively easy to construct. It didn't require any complex structures to be built in some plants in the country. So most of the entire power plant could be constructed right on site. It didn't require the reactor pressure vessel, which is a large steel vessel that is quite complicated to construct. So the core of the reactor could be constructed right on site. The dimensions of the and another feature I wanted to talk about is that this type of reactor was not just useful for producing electricity, but it had several features that allow this to be used for military purposes. And this is not quite public. This type of reactor allowed refueling during operation. So common reactors nowadays, the boiling water reactors, require a complete shutdown of the reactor, then opening the reactor and replacing the used fuel with new one. But it requires a complete shutdown. This type of reactor could be the fuel could be exchanged during normal operation. Just those channels that are inside here were independent. So each of them could be disabled, and the fuel using the refueling machine could be replaced.
Wow,
right during operation.
Why is it not still working like that today? So the power plant has to be, the reactor has to be shut down before refueling. So wasn't this like more practical, that you could change it while it was still working?
It was practical, but most practical for military purposes, because in such, if you want to produce plutonium, then you cannot allow this material to stay for too long time inside the reactor, because then it accumulates isotopes that are not are unwanted in nuclear weapons.
So basically the government wanted the refueling to happen very often, so they could take the plutonium still in good quality out of the reactor.
Yes.
For military use. Amazing.
I'm not sure if it has been really done there, but
this reactor allows it to be done.
It allowed it. It was not the perfect one for military purposes, because there are also slightly different types, but this was a feature that was quite beneficial for such purposes. Even the director of Chernobyl nuclear power plant, Viktor Bryukhanov, said that there were premises inside the power plant that even he wasn't allowed to enter.
Oh, wow.
So this might be an indication that there were some secret areas for military purposes.
So even the director of the power plant was not allowed to enter every room in the power plant.
Yes, that's according to him.
Wow.
So the dimensions of the reactor were quite big. So it was almost 12 meters in diameter, 12 meters, and 7 meters height. There were 1,661 channels, each of them consisting of fuel bundles containing uranium enriched to 2%. The total mass of uranium in the core was almost 200 tons. this is an information that's useful to assess now. Then after the explosion, how much material has been inside and how much has been thrown out of the reactor.
Mm-hmm. Is it a normal amount of uranium, or is it like too much, or for this type
you mean
of reactor?
200 tons?
Yes, yes.
For RBMK, it's normal. It's
normal, okay.
Standard. There were also RBMK of different types, 1,500, I think, and plans for larger reactors, because this reactor could be also relatively easily extended.
Mm-hmm.
So it was scalable.
Oh, amazing.
So besides the uranium inside the core, there were also control rods. In total, there were 211 of such rods that were used to control the chain reaction, and especially to stop the reaction and reduce the reactivity inside the reactor.
Mm-hmm.
What is also a bit important is that these control rods there were different types of control rods, not just those shown in some documents, and each of those rods worked in a different regime. But we will talk about this later. This is just for general information. Besides those rods, there were also some stationary absorbers inside the reactor, which is common, especially during loading the reactor with fresh fuel. Because if the reactor is loaded with fresh fuel, the total reactivity is much higher than what could be compensated using, for example, these control rods. So there were stationary absorbers that absorb the neutrons inside the core. This was also a critical parameter, as we will see later. And in each reactor, the initial load of uranium, the core is loaded initially with fresh fuel that contains about 2% of this type of reactor had 2% enrichment of uranium fissile material. And after some time, when the irradiation inside the reactor and the chain reactions happen, the fuel is so-called burned out. So during the operation, the atoms are split and other elements are produced as a result of the chain reaction. And in this reactor in Chernobyl, there was a quite high burnout of the fuel. So a lot of those channels were already on the edge of their lifetime and close to be replaced. So 75% of the total fuel. And this is also an important factor, because the more the fuel is burned out, the more radioactivity is. So initially, if you load the fresh fuel, is also very slightly radioactive. As you can see here, for example, this is a photo showing loading the reactor with fresh fuel. These are the fuel bundles. Each of them consists of 18 fuel rods centered around the central rod. And here at the bottom is the reactor.
Is it safe, or was it safe to hold it like this, just with bare hands?
For fresh fuel, it's safe. Because it's only very slightly radioactive. Most of the radiation is only alpha radiation with very low gamma emissions. So that's why those engineers can hold it in the hands. If this would be the spent fuel, those guys would be already dead.
Mm-hmm. Wow.
It would mean it would take just a few seconds or minutes to.
There is the huge difference between the used fuel and the very new fuel. So,
yes.
Wow.
This is a very large difference. So, and as we have seen, then there were 75% of the fuel already quite used. Yes, and this is a view of the reactor hall, the so-called central hall. This is the top lid of the reactor, where you can see each of those channels penetrating 7 meters plus the biological shield and the upper steam lines. And this is the refueling machine used to extract the used fuel from the bottom of the reactor.
So on the right side, we basically see the guys putting the new fuel in.
Yes.
And on the left side is basically taking the old fuel out.
Yes, maybe they are. I don't think they are now doing this, because those persons wouldn't be here, because the used fuel is extremely radioactive and all persons there might not be present
any
persons inside, because also during the replacing the radiation, background is quite high also in the central hall. And what you can see here in the background, I'm not sure if these are either fresh fuel bundles or control rods, but for sure.
But we can see the height. We can see how high they actually are. Amazing.
There were also spent fuel pools somewhere here. I'm not sure about the exact position, which were holding the spent fuel elements inside a water tank. Here we can see a photo of the construction of the reactor. This is the upper part of the reactor, where the steam lines are coming from the bottom, and this is the upper part of the reactor. Here we can see, this is a unique photo of the inside of the reactor during construction. These are the graphite blocks, and at the top and bottom of the reactor there were a few steel blocks, and they are placed around. They have a hole in the center, and these are the technological channels which inside hold the fuel bundles. And inside these technological channels there is also water circulating. The reaction inside this reactor is moderated by graphite. This means that the neutrons produced in the nuclear fission inside the fuel bundles are slowed down using graphite. So they, because for the reaction to be effective, the neutrons produced inside the chain reaction need to be slowed down their energy needs to be reduced so they can cause another fissions. I don't want to talk much about further details, but important is that graphite is used to moderate the reaction, so actually raise the reactivity, and water, which is circulating here, is used to remove heat from the fuel elements, and also water acts like a small moderator also, but also an absorber of neutrons. So also the flow rate inside the technological channels was used to control the reaction and to reduce the reactivity. Mm-hmm. Now we come to one of those dangerous properties of this reactor. If the water is heated, then steam is produced, and also void bubbles can occur in the water. And as we will see later, the void bubbles cause a rise in reactivity against water. So water is actually causing reducing of reactivity, but if it heats up, it produces bubbles, and those bubbles increase the reactivity. And the difference between water and air is about 20 times. So this is a quite large difference, which is important for maintaining the stability of the reactor. And now, if you imagine, if you have a reactor that starts to boil water, this produces more reactivity, and more reactivity results in more reactions, more fissions, and this causes again even more bubbles to produce. And if this is not controlled properly, then it can get out of control very easily and very quickly, and cause an explosion. So now we are going to talk actually what was happening during the April 25th and 6th.
I would just like to skip into your speech. What can we see on the right side, because it looks like a huge thing, amazing.
Yes, these are the main circulation pumps.
So what do they do?
They pump water from the steam separators back into the reactor. These are very important devices, very large. The person is probably of this height. So,
do you know how many of these pumps were in the power plant?
There were 4 pumps on each side, one on the southern and one set on the southern, and another set of 4 pumps on the northern side. So 8 total. During normal,
for power plant or for the reactor?
For one block.
Oh, for one block.
So each block had 8 pumps, and during normal operation, 3 of each on each side were operating, and one was on standby.
Wow, amazing, amazing piece of machinery.
Huge machines, really, really huge and complicated machines. So, what during the April 25th and 6th, there was a test planned to be performed with the fourth block in Chernobyl. And these are two main tasks. One of them was to perform a test and determine if a total loss of power would happen to the power plant, and the supply of electricity would no longer exist if the running down turbine producing electricity, because it has a certain inertia, this turbine, if it could hold the enough inertia to produce electricity for approximately 1 minute until the backup diesel generators start and can then power up the circulation pumps and circulate water through the reactor. This was one of the points, and the other one was to measure vibration characteristics of the turbine. This was more or less a standard procedure that was done every time the reactor was stopped, the block was stopped. But this time it was a bit special because for these vibrational measurements, there was a special car from Western Germany, a Mercedes car, parked inside the turbine hall.
Really?
Yes, this was probably a unique car, the only one in the entire USSR that contained a lot of electronics, latest devices and precise devices that could measure the vibrational characteristics of the turbine.
So they parked a Mercedes car in the reactor hall?
Not in the reactor hall, but in the turbine hall.
In the turbine hall?
Yes.
To measure with all various kinds of technology to measure the vibrations?
Yes.
Wow. Why did they choose a Mercedes car? Why not Volga?
I don't know the reason, but the fact that such a special device was present there was also one of, most probably it was one of the factors why they have pushed to perform this experiment, not to postpone it until a better time. So
that's an amazing piece of information. I've never heard about it. I thought it's a legend only. But...
No, it's true.
Wow.
And this was done. This measurement was done by another company from Kiev, Energo. So we have two tasks for the night of April 25th to perform. So let's go. Here we can see the persons that were directly the most famous and important persons present in the control room of the fourth block.
So basically there were not just few people, as we can see usually in the documents, like 3-4 people, but much more people involved.
Yes, much more people. The task was quite complex and several departments were involved, not just the control room, but all other rooms around the block, inside the block, they were preparing for the experiment. So usually the most important person inside the control room is the NSB, Unit Shift Chief, which was during the night of 26 April.
What does that NSB mean?
This is in Russian, so.
It means the unit, the unit shift chief.
Unit shift chief.
Okay, so that's just an abbreviation for what he actually does.
Yes, that's an abbreviation from Russian. Начальник смены блока. Начальник. So Alexander Akimov was the NSB during the fateful night. Then second person which was controlling the reactor was a very young guy, Leonid Toptunov.
So on the third one from left?
Yes. Then we have other people because the control room was quite large and required a lot of persons to control all the measurement devices and the devices for controlling the reactor and other sections like turbine shop, Igor Kirschenbaum. Then we have Boris Tolyarchuk who controlled the pumps. He's still alive as far as I know.
Oh,
yeah.
So did these people die, or do we know something about them?
Most of them. Some of them died, some survived. Depends on what were the actions after the explosion. So if they avoided premises or rooms which were highly contaminated, then some of them survived. Also, rising doublet by survived, as far as I know.
Who is the most famous one?
Most famous is most probably Anatoly Dyatlov. He held a very high position inside the power plant because he was a deputy chief engineer. Above him was only Nikolai Fomin, who was the chief engineer of the entire power plant, and the director of power plant, Viktor Bryukhanov. There were, as far as I know, 3 deputy chief engineers, so Anatoly Dyatlov was one of them. He was also a very skilled nuclear physicist who had strong experience in nuclear physics and understood a lot of processes that were happening, because there were claims that several people inside the management thought that the nuclear reactors are very easy to control, that it's like a samovar or it's similar to thermal power plants, but this is not true. Actually, the chief engineer, Nikolai Fomin, wasn't a nuclear physicist.
How is that possible?
No, it's possible.
So the chief engineer of the nuclear power plant was not a nuclear physicist?
Yes. I don't think there was a strong requirement for some positions, especially the director, like Viktor Bryukhanov. He really didn't need to understand nuclear physics into.
So he was like, so in today's language, he would be like a people manager. So he was just managing.
He had to manage several other things, including building Pripyat and managing millions of other tasks, so it was not required. There were several different departments inside the.
So technically speaking, Dyatlov was probably the guy that understood the nuclear power and the reactor the most from the high top management of the power plant.
I don't think so, because there were also other departments inside the structure of the power plant. There were, for example, the nuclear physics laboratory headed by Alexander Gobov. And he said those were the people that were always required during transient regimes in the reactor, and when there were some changes performed to nuclear devices, they had to examine this and approve. So there were also other departments that had much more skilled persons. And we will talk about this later, because actually one of those persons should have been during the night on April 26th present, but it wasn't. So from the staff that was present during that time, it was Anatoly Dyatlov, and his position allowed him to issue orders to actually anyone, because without him, Alexander Akimov would be the boss inside the control room.
So Anatoly Dyatlov became the most famous because he was basically the highest ranked employee of the power plant that night, when no one was higher than him on duty.
Yes, on duty, yes, that's right. So we have also some other persons. Pyotr Palmarchuk, Yuri Tregub, who stayed from the previous night, and ensured trainees. This was also an important person, Gennady Metlenko, because he was managing also a part of the test. So let's go now to actually what happened during the test. The test was originally planned to happen on 25th of April, and actually at 1 hour in the night, they started reducing power. The usual power of the nominal power of the reactor was 3,200 megawatts, and it was required to reduce this power to 700, from 700 to 1,000 megawatts thermal. So at 1, they started reducing the power. In 3 hours later, the power was already at 50% of the nominal power, and they performed the first measurements of the turbines, because they required these measurements at different power levels. I can skip this to go faster.
So here we can also see the shifts. So who was basically leading during those hours?
Yes, on 25th in the morning, Igor Kazachkov took the shift as the NSB of the block. They disconnected the turbine generator number 7, and they disconnected an emergency core cooling system. This was much criticized in a lot of Western media, that they disabled safety systems, and this was the reason of the accident, but it's actually not true, because, for example, this one system, when disabled, it wouldn't even come to action during the accident.
Okay, so this is an emergency
core cooling
system which they disabled.
Yes.
But even if it would be still like functioning and connected, it
wouldn't
wouldn't start up.
Yes.
Wow.
It didn't have any chance to start up, or if it would start up, it would be so late that it wouldn't do anything.
Why would it be so late? How come?
This is a bit complex too, because we will talk about this a bit later.
Okay.
during the what actually happened. So we can say that this was not contributing to the accident. Then an important event happened, that they originally planned to perform the test during the 25th of April, but they had a request from Kiev power grid controller not to reduce power further, because there was a problem in some other power plant, and they had insufficient electricity in the grid.
Yeah.
So they required them to postpone the experiment.
Yeah, one has to remember that basically the biggest feast, or the biggest day of the Eastern Bloc, or of the communist era, was the 1st of May, which is the day of labor, or day of work, as we call it. It's actually still a holiday, a vacation day in many of those countries, and on this day, the most of the production has to be on limits, or even beyond the limits. So all the production of machinery, clothes, and everything else has to be 100%, if not more. So basically, if we're reducing the production of the Chernobyl power plant, and there is another power plant which is as well not functioning on 100%, then Kiev region was not having sufficient electricity to maintain the production of all the factories. That's why it was basically postponed, and it was instructed to wait for Dyatlov, so for the night shift again.
Yeah. So in the afternoon at 4 p.m., Yuri Tregup took the shift from Igor Kazachkov, and then finally at 11 p.m. they received the OK from Kiev Energo to continue with power reduction. So they continued, and at midnight of 26th of April, finally Dyatlov arrived, because he wasn't originally present in the room, and Alexander Fyodorovich Akimov took the shift from Yuri Tregup, and they then decided to further reduce the power, and that shortly after midnight the power was about 700 megawatts thermal.
So they basically reached the goal.
Yeah, that was actually what was envisioned in the program. But then happened something that it's difficult to explain, because we don't have proofs of who actually made this decision and why. But there was another power reduction happening from the 700 megawatts down to 200 megawatts requested. And it's difficult to prove now who gave this command, because the most important persons are no longer alive, like Akimov or Toptunov. Dyatlov wrote his memories, and he said that he wasn't even present in the control room, that he arrived shortly after at midnight, and shortly after midnight he left the control room of the 4th block for inspection of the power plant. And he claims that it was probably Tregup or Rogoshkin who gave the command, but other witnesses say that it was actually Dyatlov who gave this command.
But we don't know why. So to sum it up, basically they reached the goal of 720 megawatts. So the test was actually successful.
No, they haven't started with the test yet. They only reduced the power to the desired level, but the test was still ahead.
And then someone, probably Dyatlov, decided to reduce the power even more to 200 megawatts, and we don't know why.
Well, Dyatlov said that the required level of between 700 and 1000 megawatt was not mandatory. He said that it was only the maximum level, and I don't know, maybe he felt uncomfortable with such high power of the reactor. But as we will see later, because usually people think that the higher the power is, the more dangerous it is. But this was not the case of the Chernobyl reactor, RBMK. On the contrary, the much more dangerous mode was running at lower power.
Oh, okay. So Dyatlov basically ran the power plant into much more dangerous waters.
Yes, and actually no one of those persons were aware of this danger, because usually the reactor was operated at nominal power, and the desire was always to stay at the highest possible level. And also the scientific and advisors, the Atomic Commission, and all operating manuals